You're watching a Channel 98 NBISD TV production.
Hey, welcome to another brand new episode of That Geometry Show. As always, I'm your host, Kevin Corpy. Today's show is going to be really good. Big occasion. We even cleaned the glass tile right behind us just in honor of this occasion. It was getting kind of dingy looking. Now, if you've ever asked the musical question, will the circle be unbroken? Well, you've tuned into the right episode today. We may not answer the question, but we are going to be talking all about circles. So, I promise not to sing anymore if you promise to download the worksheets and stay tuned to the show and do some math with me today. All right? Let's get right to it. Lesson 27. I thought it'd never arrive. It's going to go with your Glencoe book, chapters 9.1 and 9.2. So 2 lessons today. Circles, angles, not angels, angles, and arcs. All right. Now, what would our world be without circles? Not really a rhetorical question. If you really think about it, it's kind of quite sad. Car tires, CDs, DVDs, which, by the way, the DVDs for this show are available for checkout at the New Braunfels High School Library. Gears are circular, and crop circles, too. The circle is all around us, and we couldn't really live without it. It's one of the most useful and important of all the geometric shapes. Well, we have already seen on previous episodes that a circle is a cross-section of a cone. It was on one of the Say Whats. We did cross-sections of cones, and the cross-section, one of the types was the circle, and we can also say that cutting a cylinder sideways would also produce a circle. But what else do we know about a circle? Well, they're round. Circles are round. They're also circularly-ish, which is a very precise mathematical term in my head. It's not a real term. And circles are also very round. So, yeah, that's good. Let's get more precise, more rigorous here. Here is a mathematical definition known as a locus definition of a circle. Now, locus just means that we're going to start our definition with the set of all points. Okay? So the circle is defined mathematically to be the set of all points in a two-dimensional plane that are a given distance r from a given point A, a fixed point A in that plane. So if I look at this diagram here, A would be the fixed point. R would really end up being the radius. And if I go out that same distance in all directions from A, the length of the radius, and I do it infinitely many times, I will trace out these ordered pairs or these points that define the perimeter, or what we're going to learn today is the circumference of the circle. Okay? So that's the locus definition. It's worth memorizing. So again, R is the radius, and A in this case is what we're defining the center of the circle to be. Now, circles are usually named by their center, and we have a special symbol for them. So in this circle right here, C is the center, not A. We're going to call this one circle C. So it's just a little circle itself with a point in the middle representing the circle. So that's the symbol for circle, followed by the capital letter, which is the point that is the center. So the center is C, and the radius in this case, since I'm defining it by points, would be the line segment that's drawn, either CB, which is the same as BC, or segment CA, which is equivalent to AC. And remember, a segment has the bar above it, so CA or CB. Now, we've been talking about diameter on previous episodes. The diameter is related to the radius. The diameter is twice the length of the radius. It passes through the center, and it goes from one side to the other. So if this is the radius and this is the radius, the diameter would be twice the radius, or the radius, you could equivalently say, is half the length of the diameter. Okay? So what else do we want to know about circles? Well, circles are also what we call simple closed surfaces. And we've talked about closed surfaces on a previous episode. And they actually divide the plane into an interior and an exterior. So the interior of the circle would be everything inside. The exterior would be everything outside. The circumference, which we've also seen on previous episodes, is really the distance all the way around the circle. If you were to walk all the way around, it would be the total distance that you've traveled. It does have a formula, and here it is. We're going to call capital C the circumference, and it's equal to 2 times pi. And remember, pi is just approximately 3.14, and we'll be getting back to pi later in the show, times the length of the radius. Now we can also get an equivalent formula because we know that 2 times the radius, by definition, is the diameter, which I'll call little d. I can replace the 2r in this equation with d, and I also get that the circumference is equal to pi d, or pi times the diameter. So depending on the information that you're given, if you're given the radius or the diameter, there's 2 simple equations that you can use to find the circumference. Now, the circumference, the diameter, and the radii are all measurable lengths, and they're measured in linear units, such as inches or centimeters or miles or furlongs, if you still use that unit. Now, how many radii, which is plural of radius, does any given circle have? I'm glad you might have asked that, if you did. Well, a circle has infinitely many. If I start from the center here, I can go out from the center as many lines as I can tolerate to draw and land on the outside of the perimeter of the circle, and those would all be radii. And even if I draw them as close together as I can, there's probably infinitely many in between those two that I can't physically draw, but they're still there. Okay, and they all start at the center and pass to the outside. And because of that, we can also draw straight lines all the way across through the center. Those would be diameters, and there's also infinitely many of them. Now, before I started drawing on this, you might have said, hey, I've seen one of those outside of my garage, that thing that I should ride more often that I really don't get enough time to do. It's a bicycle. Okay, and the bicycle out there is not only a good form of exercise, but the wheels have very noticeable radii on them. The wheels themselves are circles. What would we do without circles for wheels? It would be a much more vigorous exercise. But the spokes in the wheel themselves can be thought of as a radius. Now, speaking of diameters, let's combine it with food, which always makes math much more interesting. A 9-inch pizza, a 12-inch pizza, that's typically how they size the pizzas and price the pizzas. Well, that 9-inch represents the diameter of a pizza. So if we slice a pizza all the way across through the center of the pizza, I can almost smell it, even though it's not even scratch and sniff. That looks good. The diameter is all the way across, and that's what the 9 is measuring in this case. So a 9-inch pizza has a diameter of 9 inches. Okay? Now, we need to get through the show so everyone can go raid the freezer and put in a pizza. I know. Let's look at some examples and put all this into good practice. Now, we're going to start with some real easy examples, and I don't mean to be insulting you out there, but we're going to work up some steam gradually. Okay? Here's the first example. We're given a circle here, and we are told that the radius is 2 inches. What is the diameter? Well, remember that the diameter is all the way across, or 2 lengths of the radius. So we can use the formula diameter d is 2 times r, and we just plug in. So the diameter is 2 times 2 inches, which is 4 inches. Now, a word about units. If there are units given, in this case they are inches, you want to include inches in your final answer. If you don't put them in the interior, that's okay, but make sure you put them at the end. It's a good habit to get into. So that was pretty easy. Just double the radius. Number 2, the radius of a circle is 2 inches. What is the circumference? Ooh, wow. We're having to find a different quantity now, not the diameter, and we're still given the radius. Well, we're looking for the circumference, and I know the radius. So I want to pull out the equation of the formula that has them both in there. Remember, there were 2 versions. We had 2 times pi times the radius, and the other one was pi times the diameter. So I'll just plug in. 2 is a constant. Remember, pi is a constant. It's about 3.14, but I'm going to leave it as pi, times 2 inches. Now, the exact answer would be 2 times 2, or 4 pi inches. If you want to get an approximation, you can multiply 4 by 3.14, or your TI-83 calculators also have a pi button on there, and you can get a more, not a better approximation, which would be about 12.566 inches. And on this show, I typically go to 3 decimal places every time, although you might not have to go that far in the classroom or on a test. All right? Next one. The diameter of a circle is 3 centimeters. What is the circumference? Well, that's a little bit different from the last one in the sense that we have now the diameter, which is all the way across. So I can use the formula for the circumference that has the diameter in it, which is just pi times the diameter. Okay? So let's plug in. Pi is pi, 3.14. The diameter now is 3 centimeters, And so the final answer is really 3 pi centimeters. That's exact. And that is approximately, if you plug it into your calculator, 9.425. And again, we've switched from inches to metric here, centimeters. So there's your final answer. All right, so those have been pretty easy. Let's look at this one here. We're kind of working backwards on this one. We're given the circumference of a circle to be 15.7 centimeters, and we want to know the diameter. Well, again, the two things involved are circumference and diameter. So I'm going to still use the same formula. And remember, these are literal equations, so as long as I know one of the two unknowns, I can solve for the other. In this case, I can plug in 15.7 centimeters equals pi times d. Remember, pi is a constant, so dividing both sides by pi, I get d is 15.7 divided by pi, which works out to be about 4.997 centimeters, which is pretty darn close to 5 centimeters. Okay? And that would be the diameter all the way across. So the radius, this is not written, but the radius would be half of that, or 2.5 centimeters. All right? Let's look at the applications of the circle now. All right, back to that crazy bicycle. You're just going to keep reminding me that I need to get out there and ride it more often, right? Yeah. Well, let's look at an application that involves a bicycle. If we know that the diameter of your bicycle wheel is 25 inches, okay, that's all the way across through the center, how far will you move on the street in the forward direction, okay, in this direction, when the wheel turns one time, in one turn of the wheel? Wow, well, this one requires a little bit of thinking. As my old algebra teacher, Mr. Kensing, used to say, this one is a woolly booger. Well, thanks for watching the show, Mr. Kensing. This one is actually not as bad as it seems if you understand what it is you're looking for. And here's the key insight. The linear distance that you move forward on the street is going to be the same as the rotation of the tire once around. If you took this tire and cut it and laid it flat on the street, you would be staring at a certain distance here, which is actually the circumference of the tire. So the circumference is what we're looking for. Okay? So let's go ahead and pull out the equation that deals with circumference and diameter again, and it's pi times d. So the diameter is 25. I just plug it in. 25 pi centimeters, or sorry, we're on inches this time. My bad. And that works out to be around 78.540 inches. So on that bicycle, when the tire turns one time, you're moving that far down the street. Which basically means if you want to ride your bike 1 mile, you're going to have to go make that tire go around about 807 times to make 1 mile. Okay? So that kind of puts it all in perspective. Now an extension. We're going to have to work a little harder. And look, I got a little friend here, a little bug who wants to learn some math. Okay, I'm going to push him off to the side gently. Come back later. All right, here's the extension. We want to refer to circles B and circles D in this figure. We know that this length BC is 5, and we know that this length CD is also 5. Okay, we want to find what the length of segment AE is. Well, let's look at it. From B to C, that segment, that's just the radius of circle B. So the radius of circle B, which I'll write again as that symbol, B, it equals 5. Well, from B to D, that's the radius of circle D. So the radius of circle D is going to be this 5 plus that 5, or 10. Now, we can use that to help us find the other dimensions. From A to B is just another radius of circle B, so that has to be 5. And from D to E is just another radius of circle D, which we already found to be 10. Now I have all these discrete segments labeled from A to E. I just add them up. We can do that in our head. Let's try it. 5 plus 5 plus 5 is 15, plus 10 is 25. So AE equals 25. And were we given units? Look for units. Inches, centimeters, furlongs, nothing. So we might put units here just to be thorough. But it is 25 units across. All right, as always, it's time for a quick break. Don't go away. Watch these public service announcements, and I will be right back here waiting for you.
I smoked weed, and nobody died. I didn't get into a car accident. I didn't OD on heroin the next day. Nothing happened. We sat on Pete's couch for 11 hours. Now what's going to happen on Pete's couch? Nothing. You have a better shot of dying out there in the real world. Driving hard to the rim, ice skating with a girl. Now you want to keep yourself alive, you go over to Pete, sit on his couch till you're 86. Safest thing in the world. Me? I'll take my chances out there. Call me reckless.
All right, welcome back. We got to jump right back into our lesson on circles today. There's an important theorem waiting for us. Let's not let it wait any longer. It'll get angry. Urgh. Okay, now circles have other parts as well that we're going to look at today. The first one is an arc. Now an arc is any continuous portion of a circle. For instance, over here I have this part of the circumference from point A to point B. We call that an arc. It's basically a portion of the circumference of a circle. And we're going to get back to how to name those later on. A chord is another part of a circle, and a chord is basically a straight line whose endpoints are on the perimeter or the circumference of the circle itself. And you spell it with an H right there. It's hard to see. Now, the chord can actually pass through any 2 points like that, and it could come in at a weird angle like that. So a diameter, believe it or not, because there are infinitely many diameters, we say a diameter, which passes through the center, is technically a chord as well. And it's actually the longest chord in the circle. Now here's a question to you. Is a radius also a chord? Tick, tock, tick, tock, tick, tock. Well, we don't have much time for you to think any longer. I'll give you the answer. The radius is not a chord because although one of its endpoints is on the circle, remember a radius's other endpoint is at the center of the circle. And the center of a circle is technically not part of the circle itself. Okay? It's an important characteristic of the circle, but it's not on the circumference. So the radius is not a diameter, it is a chord. Now, we're going to kind of look more exclusively at arcs here. Every single arc, when you trace it out along the circumference, will have what we call a central angle. When you draw the endpoints of the arc back to the center, you get this angle right here, which we're going to call theta. So this is a Greek letter, theta, and we use it to represent an angle or an angle measure, the name of the angle or its measure. We're going to later start calling arcs lengths S, so we could say this arc S subtends, that's a fancy word, subtends an angle of theta. Okay? So an arc length is part of a circumference, and the central angle is basically an angle that's carved out from a circle. All right? So what we want to do is we want to look at the measure of the arc itself. Now here's the thing about the measure of an arc. The measure of an arc is nothing more than the measure of the central angle. I'm going to write that down here. The measure of an arc, which we're going to measure in terms of the central angle. Measure of the central angle. And we measure angles in degrees. So the measure of the arc itself, although it's a piece of the circumference, which you would think would be linear, we're going to say the measure is in degrees. Now later on, we're going to get into the arc length. The arc length is going to be a portion of the circumference. And that's going to be a linear length, like centimeters. We're going to say this arc is like 5 inches long. But the measure of the arc is always in degrees. And it's very important to get those two straight. Okay? Now, another important thing is the fact that the central angles, if we go all the way around, have to add to 360 degrees. All right? So what that means, if you have a radius in a circle that comes up from the center, and you sweep all the way around, let me draw a circle here. Here's the center, here's the radius. If I rotate all the way around to get back to my starting point, I will have rotated through 360 degrees. So that would be an arc length that actually is, in fact, the circumference. So one rotation, you can say, is 360 degrees. And sometimes we use revolution as well. One revolution or one rotation around the circle is 360 degrees. And so that's the sum of all the central angles. Now back to the naming of the arcs. We're going to use 2 letters to define most of the arcs. And remember, for line segments, we put a bar across them. For an arc, we're going to put kind of a little piece of an arc above it. So I'll make this larger so you can see it. In this diagram down here, I have circle A, and I can look at the arc, that's a piece of the circumference from X to Y. We're going to call that, right here, the name would be XY, and we can put the arc over it. And that's going to be equivalent or congruent to YX. So in this case, the order doesn't matter, but they do get an arc above it. Now, there is another arc that is in this circle that would extend all the way from X around this direction and still end up back at Y. That's a larger arc, and notice it also passes through point Z. This gives us a way to classify the types of arcs that we have into a minor arc and a major arc. A minor arc is a central angle that is less than, and I made a mistake here, so I'll fix it now, and I'll fix the key when you download them, it'll be correct. It's less than 180 degrees. So remember, 180 degrees is our straight angle. It's right here. So any arc that is less than half the circle is less than 180 degrees. It's a minor arc. So XY, arc XY, would be a minor arc. And a major arc, then, is an arc whose central angle is greater than 180 degrees. So this arc here would be a major arc. Now, major arcs, because they are greater than 180 degrees, there we go, we use 3 letters to denote them. And so we need this other point Z. If I just said arc XY and the Z wasn't there, you might be confused. Is it this minor arc or is it the major arc that still goes from X to Y? So this would be a minor arc, and that's why for a major arc we always add in one other point. We call it Z. So this would be arc XZY with an arc over it, or it's equivalent to YZX with an arc over it. So that's how we name the arcs. Now, here's some things to recognize or realize about that. The measure of the major arc is really 360 degrees minus the measure of the minor arc if we just have the 2 arcs. So if the major and minor arcs are actually the same, which would occur like this. Here would be maybe one arc, which would be 180 degrees because the central angle is 180. And the other arc would be 360 minus that, which also makes it 180. So what happens if neither one of them are greater than or less than 180, but equal to 180? Well, that's a special case, and we call both of those arcs semicircles. Okay? Semi, not because it has 18 wheels like a semi-truck, but semi because it means half. Okay? It's half the circle, half the circumference. So we got minor arcs, major arcs, and semicircles. All right? Now, we can also assume then that the sum of each of the major and minor arcs, if there's only 2, equals 1 full rotation, or 360 degrees. Here's an example. In circle P, we know the measure of angle QPR, where P is the center. How do we know P is the center? Because that's what was given in the name. So this angle here, angle QPR, is a central angle. And if we know that it's 40 degrees, we want to find the measure of arc QR, which is right here. Now remember, the measure of an arc again is in degrees, and it's measured in the same degree as the central angle. So it's also a 40-degree measure. Okay, so this equals 40 degrees. The measure of an arc is in degrees. Got it? Pretty easy example. Let's go a little bit further here. It's not written here, but let's go ahead and figure out what the measure of arc RZQ is. It's going to be this longer one that goes all the way around the outside here. Remember that the arcs have to add to 360. So this one must be 360 degrees minus the measure of arc QR, which we just found to be 40 degrees. And so that gives us 320 degrees. So let's classify them now. Arc QR is going to end up being a minor arc because it was less than 180, and arc RZQ ended up being a major arc because it was greater than 180 degrees. Got it? All right, sometimes our examples require algebra. Here's an algebraic example, and if there was a woolly booger on this one, this might be it because maybe algebra and x's scare you a little bit. So in circle E, that's the center, we know the measure of angle AEB, this one here, is 4x plus 18. And we know the measure of angle BEC is going to be 5x plus 4. And we also know CED, that central angle, has a measure of 3x plus 4. And then finally AED that central angle has a measure of 5x minus 6. Now, of course, as always, we're going to first try to find x. So notice that all these central angles complete one full rotation of the circle. So the sum of all these expressions has to equal 360. So I can set that up. 4x plus 18 plus 5x minus 6, working around, plus 3x plus 4 plus 5x plus 4, that's adding all these up, has to equal 360 degrees. Okay? Now it's an algebra problem. I can go through and I can collect all my x's, and if I do that, I'll have 4 plus 5 is 9, 12, 17. 17x, and adding up the numbers, I'm going to get 20. So plus 20 equals 360, and then subtracting 20, I get 340, and then dividing 340 divided by 17 is 20. So x is 20. Okay, so now what I want to do is I want to find the measure of arc DAB, which I'll draw it. It's this one right here. So notice that it's the sum of arc DA and arc AB. So if I know those expressions and I know what x is, I can go ahead and find it. So the measure of arc DAB is going to be 5 times x minus 6. That's this one here. But I know x is 20. Plus 4x plus 18. 4x plus 18. But again, I know x. I just found it to be 20. So if I add all those up, we're kind of running out of time. We get 182, and let's classify it now. Now notice from the picture, if I turn it this way, you can see that it looks like it's a little bit bigger than 180 degrees, or possibly what we call the reflex angle. But again, you don't want to go just on the diagram and say, because it looks bigger than 180, it is. The numbers don't lie. It is, in fact, bigger than 180. It's 182, only by 2 degrees. So this is a major arc. All right, now it's time for the say what? And we got to do this a little quickly today because we are running out of time. It's Archimedes Part 3. Archimedes really loved circles. Remember when they invaded Syracuse, he asked the guard, please don't disturb my circles. He was also one of the first to build elaborate, use gears to make elaborate clocks and calendars, and he even built the first odometer using circular gears. But he was also the first to give us a theoretical calculated rather than a measured version of pi. He gave us a lower bound of 3 and 10/70ths and an upper bound of 3 and 10/71, which in decimals is 3.1428 and 3.1408, which is actually pretty close. It's close to exactly 2 decimal places. The real number is 3.159. So back then in 300 BC, that was remarkable that he did that. Okay? Now you've probably been saying this whole time, what is pi? What is pi? Well, if we take the equation circumference equals pi times d and I solve it for pi, I get pi is the circumference divided by the diameter. So that means pi is the constant ratio between any circle's circumference to its diameter. And that's something you can do at home. You can take any ball, any circle. If your brother is Charlie Brown, you can even take his head and you can measure the circumference of the circle and measure its diameter and divide the circumference divided by the diameter, and you should get something very close to 3.14. It is a really fun activity to do, and you can do it right from home. Okay? That's all we have time for today. So there is another sheet. If you want to look at it, you can download the website from the website, and there's 2 nice links here that describe how Archimedes was able to do that. Whew! I'm kind of worn out today. You know, I'm wondering if hosting a 30-minute geometry show and trying to pack in 40 minutes of information into a 30-minute show can be considered a method of exhaustion. I don't know. Well, anyway, that is all the time we have for today. So until next time, I'm Kevin Corpy, and I will catch you on the flip side.